Hello all. You have got a sensor that is giving you garbage values not because of it is broken, but because it listens to the noise instead of signals. If you are using AURIX but you have used only VADC so far, then you are missing something. I'll show you how DSADC see through the noise, but VADC cannot. This is COCOWATT Media, where we turn AURIX theory into real world proof. We have got a packed agenda, but don't worry, we will take it step by step. We will begin with a quick comparison between VADC and Delta-Sigma ADC. Then we will explore the DSADC generic architecture, how each stages work, followed by a AURIX DSADC key features and its architecture. Next, we will go through the step-by-step configuration and code walkthrough, and finally wrap up with the live demo. In the earlier session of AURIX microcontrollers, we have covered AURIX architecture, GPIO, VADC, and its live demo, along with other important topics. If you missed it, make sure to check it out. If you ever wonder which ADC to choose for your project, this one is for you. Let's start with the successive approximation ADC or SAR ADC. These are like sprinters of ADC world. They grab a snapshot of your signal in few microseconds. They are fast, accurate enough, and great when timing matters. Perfect things like motor control, real-time feedback, or high-speed data logging. Now, let's talk about Delta Sigma ADC or DSADC. These are more like a marathon runner. They take their time, oversample the signal, and then filter it digitally. The result is super smooth, precise, and low noise reading. They are perfect for slow changing signals like temperature, battery voltage, and audio measurement. Accuracy and stability over time is their strength. So, here is the takeaway. If you need a speed, go for SAR ADC. If you need precision, go with Delta Sigma ADC. Let's look at how Delta Sigma ADC works. First, the analog input. This is your real world signal, maybe from a sensor or a battery. It is continuous and may have some noise. Next, the digital signal modulator. Instead of taking one quick reading like a SAR ADC, it samples the signal millions of times per second and output only one bit data stream like ones or zero. Think of it as a very fast high-low switch. Then comes to the digital filter. It cleans up the noisy data stream, remove the unwanted frequencies, and averages the data to get a smooth and accurate signal. After that, the decimator slows the data rate down to something useful for your system while keeping the accuracy ahead. Finally, the result register holds the clean digital value ready for your microcontroller or a CPU to use. And that's the flow of Delta Sigma ADC, starting with the noisy analog signal and ending with the clean, high precision digital value. Simple, right? Alright, let's talk about how Delta Sigma ADCs are actually built inside the AURIX TC27x, because this is not just a one little block, it's a whole subsystem, and it designed for real world and safety critical application. Think of it like this. Instead of having a one ADC doing everything, the AURIX gives you multiple independent channels, each acting like its own mini ADC. That means each channel has its own register, its own setting, and can run independently on its own. So, if you are measuring a motor current on one channel and battery voltage on another, there will be no interference, no waiting. They work in parallel. Now, inside each channel, there are two main parts and they serve very different purposes. First, the main part. This is where you get the high precision results. It starts with the modulator, then comes with the digital filtering. First, CAR filter, then FAR filters, maybe even offset compensation and an integrator if you need it. All that cleanup leads to the result register with the clean, accurate, high resolution value, perfect for when precision matter most. But here's the clever part. Every channel also has an auxiliary port. Think of it like a built-in watchdog. It is simpler, just a quick CAR filter and a comparator. Its job constantly monitor if your signal goes outside the safe limit, like detecting overcurrent or voltage or temperature spikes. The moment it spots something wrong, it triggers the alarm or a service request instantly. It is super useful in safety systems, motor control, or any application where you can't afford to miss a fault. And don't forget the and don't forget the whole thing runs off the clock And don't forget, the whole thing runs off the clock source that comes from either system clock or internal oscillator. You have got the flexibility there, right? We have already covered the basic architecture of Delta Sigma ADC. Here we see how the Delta Sigma ADC implemented in AURIX TC27x. Here we have a modulator that converts analog to digital 1-bit stream with the 10 to 20 megahertz of frequency. And then we have a CIC filter which is act like a primary decimation filter. The decimation rate is 4 to 128. And here we have two FAR filters to fine tune the frequency response. We can able to enable one or two depends on the configuration. And there was one more module called integrator for specific apps like resolver or shunt current measurement. And again, we have a carrier generator which is very useful for the resolver application. And at the end, we have a digital reset register which can be directly read via CPU or configured with the DMA to copy a data without CPU intervention. Here are some key features of AURIX DSADC. You can connect a differential input for noise immunity or single-ended for simplicity. Need to measure a tiny voltage? Turn up the gain. Worried about power? Switch to standard mode. The built-in calibration helps to compensate the manufacturing variation. Controlling the common mode voltage is crucial for getting the best signal to noise ratio, and the common mode hole prevents the noisy signal when pins are not being used. Plus, a DMA and interrupts make it easy to handle data without burdening the CPU. The resolver support is huge bonus for motor control tasks. Configuring DSADC might seem complex at first, but it actually follows a very clear sequence. We start with the basic system setup, enabling the clock and access permission. Then we apply the global setting like clock source and run enable. After that, for each channel, we configure the analog input by selecting the pins, gain, and mode. Then set up the modulator clock and the filter chain, including both main and auxiliary parts. Finally, we start the conversion and read the result either by polling or interrupt or DMA. We walk through each of these steps in detail in code walkthrough.
Okay, let's do the code walkthrough. Before we start into the DSADC, let's understand the modules which we have configured for the demo. First, the PWM. PWM, which will be enabled to generate a PWM of 10 kHz, and this PWM will be given as a input for both VADC and ADC. And inside the while loop, I have been incrementing the PWM duty cycle by 0.5% every 100 milliseconds. Every 100 milliseconds, I'm also reading the input voltage of VADC and DSADC and send it through the serial port. Now, let's go into the initialization of VSADC. We use Infineon library to configure everything cleanly. We set a massive decimation factor of 1024. That means the DSADC oversamples at 10 megahertz. Then the digital filter averages over 1000 samples and produce ultra clean result. We enable both FAR filters for sharp noise rejection and turn on offset compensation to remove the DC drift. So first we have initialized the module by initializing the clock for the module and global configuration with the selected clock and the selected input voltage reference for the DSADC. And then we'll be initializing the channel by configuring the positive input pin, negative input pin. This negative input pin currently configured as ground since I have been using single-ended mode. So if you want to configure differential mode, we have to configure with the input pin also here. And then I have been configured the input gain with the factor of 1, and I have been using pin A as the input, and we have been configured here a 10 MHz clock modulator frequency, as well as this initialization will be updated to the register by calling the init modulator function. Will be initializing the modulator, demodulator, and the combination filter by using the decimation factor which we have configured, and FAR filter have been enabled by enabling this configuration, and integrator, auxiliary filter, and rectifier. Once we have initialized the channel, we have been initializing the global configuration run register to enable the DSADC for acquisition. Once it is enabled, we will be able to see the results in the results register, which is RESM result. So once it is once the result acquired every 100 milliseconds, it will be sent out via UART for both VADC and DSADC.
Okay, let's see the live demo in action. Here, I have generated the PWM of frequency of 10 kHz and the variable duty cycle, which will increase its duty cycle by 0.5% every 100 milliseconds. I have connected the generated PWM from port 06 to analog AN2, which is DSADC, and AN7, which is VADC. And here we can see the VADC and DSADC readings, which is sent via UART every 100 milliseconds, and it will be plotted in the COCOWATT serial monitor to see how the DSADC and VADC behaves.
Alright, let's see this in action. Here is our setup. I am running the code we just walked through, and I will switch to the graphical window. Here you can see the duty cycle which I have been updating for the PWM, and here is the same input signal which is read by the VADC and DSADC. You can see the VADC is hovering from high to low continuously, whereas VADC is purely following the duty cycle which we are applying on the pin. From this demo, we are sure that the DSADC purely demodulates the signal and filter it out and send it as output without any noise. And in the LED, you can see it is glowing from off condition to bright condition, where it shows the duty cycle is gradually increasing.
Thanks for watching. This is COCOWATT Media, where we turn AURIX theory into real-world proof. If this helped you to see through the noise, hit the like button and drop your questions in the comments, and subscribe for more embedded videos.